Hello everyone. So we'll start for today's session where we'll discuss the design of PID controllers. So as you would have gone through the lectures, you would probably have seen like the general structure of the PID controllers, but in actual practice, PID controllers are one of the most widely used controllers in the industry. Like almost all sorts of feedback applications, like wherever we want to do some feedback control, the first and foremost thing that people will try is the PID controller because of many reasons. First is it is very easy to implement. You just have to tune some three parameters, and next is so easy to implement, meaning there is less computational burden on the processor that is doing the control. And next is it is very reliable. Like it has been tried and tested for many years in the industry. So PID controllers is one of the most reliable and important used controllers in the industry. So with that, we'll begin for today's session. I will go through a set of questions which will try to help us, like we'll basically use the concepts we have learned till now, let's say root locus, border plot, or route array, simple time responsive systems, those concepts, and try to find out what kind of PID controllers we should use to get our desired objectives or like whatever requirements the system has. Okay, so with that we'll start with our first question for today. So we have a unity feedback closed loop system with a plant transfer function given by G of S, which is a standard second order system, and a controller GC of S is in the feed forward path. So essentially the open loop transfer function is GS into GC of S. Okay. So for a unit step input, the transfer function of the controller that gives the least steady state error is which of these? So what do we have? We have a given plant, a feed forward controller, and we are saying that we need we are being given a unit step input. So what kind of controller among the following options will give us the least steady state error? So for answering that, we need to find out the steady state error for a general GGS open loop transfer function. So tell me the formula for the steady state in terms of the error constants for a step input.
A by 1 plus Kp.
Sorry, K by?
A by 1
plus Kp.
This is the formula, right? 1 by 1 plus Kp?
Yes, sir.
Yeah. So where Kp is the position error constant given by limit s goes to 0, G of s, Gc of s. Yeah. So now we know G of s, so we can first find out limit s tends to 0, G of s. That gives me just 1 by 0 plus 1, that is 1. Now, so as you can see, if Kp increases, the steady state error will decrease. So essentially Kp is limit s goes to 0, Gc of s. So if this increases, then the steady state error will decrease. So we want the Gc of s among these options with the highest Kp, or that is with the highest value at limit s tends to 0. So for this, what will be the value? For this, Kp is, if you put s equals to 0, we just have 1 by 2. For this we have 2. For this we have 2 by 3. And for this, what do we have? Kp is infinity. So clearly, among these four options, the largest Kp is for Gc of s equal to s plus 2 by s. So if I wanted to design a controller in the feed forward path with just the requirement that say I have 4 possible options of controller designed for me among these, and I want to find the one that will give me the least steady state error. So then I can try this out, find whichever has the has the highest position error constant, then I can just use that controller for my system. Is this clear? Whatever we did here?
Yes, sir.
Okay. So we'll move on to the next question. Okay, now we have a plant with a transfer function given by g of s is 2 by s into s plus 3. And we are told that it is to be controlled by a PI controller with the first constant kp equal to 1 and the integral constant is just given that it should be non-negative. And the system is placed in a unity feedback configuration. So basically this PI controller is put in the feed forward path. So for what values of Ki does the system have a zero steady state error and for a step input? So again, similar to the previous question, let's say this is the controller Kp plus Ki by S, that is 1 plus Ki by S. Again the open loop transfer function here is Gs into Gc of S, and for a step input we know ESS is 1 by 1 plus Kp, with Kp being given by limit s goes to 0, the open loop transfer function. So let us find out the Kp for this. Limit s tends to 0, 2 by s into s plus 3 into Kps plus Ki by s. So what is this value?
Infinity.
Infinity. Yeah. So now you see that this is infinity. So this implies ESS is 0. Right. So here there is no particular constraint on the value of Ki for it to be for the steady state value to be negative. This is only one. For the steady state error to be non-zero. That is, for all values of Ki, we will have a zero steady state error. For all Ki greater than equal to 0, we have ESS equal to 0. So, from the questions that you have tried till now, can you tell me which kind of systems have a steady state error for unit step input?
Type 1.
Type 1. Yeah. So basically, for all system with type greater than 0, we'll have steady state error 0 for a unit step input. Now, similarly, if you go to a unit ramp input, then what do you think the type of the system should be to get a steady state error?
So type 1 and type 0 system, sir.
No, like I have a ramp input.
Type 2, sir.
Yes, correct. So since I have a ramp input, my steady state error is given by 1 by kV, and kV is limit s goes to 0, s into the open loop transfer function. So if the open loop transfer function is type 1 or type 0, then you will see that the s on the denominator will be cancelled by this. So either this value will be 0 or some constant. It won't be infinity. Since it is not infinity, the steady state error won't be 0. Okay. So in general, the more number of integrators we add to the system, we guarantee that the steady state error will be 0 for different kinds of output. Like, so if you have a simple step input, then only a single integrator in the transfer function, open loop transfer function, will get us to 0 steady state error. Now, if we have if you want to track a unit ramp, then 2 integrators will help us get to 0 steady state error. Similarly, if we have a parabola or any higher order thing, then we keep adding more integrators that will ensure that the system steady state error goes to 0. Okay, is this clear? So for this question, For all values of ki, the integral coefficient, we will have a zero steady state error for a step input. Is it clear?
Yes, it is.
Yeah. So then we move on to the next question. Now, if consider this plant given, again we have some kind of plant and a controller in feed forward path. If a proportional controller is used, that is Gc of S is equal to Kp, just this gain, then find the value of the controller gain Kp to have a steady state error of 0.25 for a unit ramp input. Right? So what did we discuss just now? We are being given a unit ramp input. So what should the steady state error be? 1 by?
1 by kV.
1 by 1 plus Kp.
No,
1 by kV.
that will be for step
1 by
input.
Kv.
Yeah. So we will have 1 by kV as a steady state error for a unit ramp. Now we want this to be 0.25. So this implies kV must be 4. Right. So since kV is 4, just a minute. Yeah. Since kV is 4, we have that. Where are we? Yeah. So what is kV? kV is we know that limit s goes to 0, s into gs into gc of s. That is the open loop transfer
Equal
function.
to 2s, sir.
Sorry, I didn't get you.
Kp equal to 2s, sir.
Kp equal to
2s.
yeah, we'll get to that. Just a minute. We'll solve this. Yeah. So this must be 4. Right. So we'll put these values. Limit s goes to 0. I have this. Gc is just Kp. So I'll then put the thing. Yeah. So this will give me. This is to be 4. So from this we get Kp is equal to 2. Correct?
Yes.
So this is how we work with control systems in the real world. Like you are given a plant, most likely the plant will be some real system whose transfer function you find using certain techniques. Either you find from the physics of the system, or you try to identify the system using system identification tools and techniques, or some other way, like you have some data or something, and from the input output things you can identify the system. After identifying the plant transfer function, now you have to decide between what kind of controller you want to use. Then for that, it will obviously depend on the plant, that is the system transfer function. Then apart from that, that will depend on your specifications. If you just want some steady state error, then you can use some basic model. If you want, apart from zero steady state error, you want some percentage overshoot to be something and rise time to be something and things like that. If you have a bunch of specifications that you need to meet, then you will just experiment with different models for controllers. Let's say you take the entire PID, KP, KI, KD. You will experiment with those things. Then you will see whichever, like you will have to most likely do a trade-off. Like probably like it would be such that for a PID controller, you are using a PID controller and you see that if a certain specification is being met, the other one is violated and vice versa. So in that case, what you'll do is you'll try to get to a trade-off point. Like I am fine if this percentage overshoot is this much and the settling time is this much. So this range works for me, so I'll choose this controller. Here there is no unique answer to, like if someone has designed a controller, then there is no single answer to this. You can be as creative and as like however you want to design it. It should just be a good enough controller that does not blow up the system, and it should satisfy your specifications within a reasonable range. Okay, so is it clear how? Yeah.
Sir, here can our limit s tends to 0 kp s into 4 so by s square plus 2s.
GC is Kp, S is here, and G is the 4 by s square plus 2s. This S is here because this is the velocity error constant.
Yes.
correct ना?
तो वैल्यू इंफिनिटी जैसे नॉमिनेटर में तो डिग्री 2 है सर, नॉमिनेटर में डिग्री 1 है, डिनोमिनेटर में 2।
हाँ like no, I don't get your question. न्यूमरेटर में डिग्री 1 है, डिनोमिनेटर में डिग्री 2 है,
2 है।
हाँ
अब लिमिट तो 0 ऐसे तो इंफिनिटी वैल्यू होगा।
नहीं, मतलब अगर ऐसा है s/s² तो लिमिट s goes to 0 क्या है? अच्छा, इसमें तो नहीं होगा।
सही है सही है सही है सही है, यस यस
हाँ, तो s कैंसिल हो जाएगा ना, तो जस्ट
यस यस।
1 होगा। या so okay, so we'll move on to the next question.
Yes, sir.
Okay, now okay, so we have the same system, right? Plant is 4 by s square plus 2s. Now I am adding only an integral controller of this one. It is added into the forward part. So now what is the steady state error to a unit ramp input? So this is again the same thing. ESS is 1 by kV. Then kV is equal to limit
Hello?
s. Yeah.
Sir, is the value of GS is given?
This is from the previous question only. Continue.
Oh,
Limit s goes to 0, s into GC of s into G of s. So this is limit s goes to 0, s into Ki by s into G of s. What is this? 4 by s square plus 2s. Now what is the value here?
4. 4 Ki is equal to 4. Infinity. Infinity, sir.
Yeah, this is infinity because the s that we had, it is cancelled and we have an extra s, right? So this is infinity. So the velocity error constant is infinity. This implies steady state error is 0 for a unit ramp input. Now here you can see, if you compare it to the previous question, there we used only a proportional controller, that is only a gain value Kp, and in the next case we used an integral controller, that is one integrator is extra in the open loop transfer function. So as we discussed earlier, by adding one integrator extra, we could go from some constant steady state error to zero steady state error, right? So if we are having a system where there is some constant steady state error and say we add one integral controller in just one integrator 1 by s, let's take, in the open loop transfer function, then we can achieve zero steady state error in that system. Okay, is it clear?
Yes okay.
Yes, okay. Yes, sir.
Yeah, so that is why integrators are a pretty, what do we say, like powerful kind of tool to get to zero steady state error. Now okay, in the same question we had g of s is equal to 4 by s square plus 2s. If a 0 is added to g of s at s equal to minus 2, which say the controller as 1, what is the velocity error constant? So now my g of s is 4 into s plus 2 by s square plus 2s. So I want to find out the velocity error constant. So tell me, what should the value be?
4.
It is limit s goes to 0, s into 4 into s plus 2
4.
by s into s plus 2. Yeah. So this thing is getting cancelled, this thing is getting cancelled, all we have is 4. So now we see, what do we see? If to the original system I add one 0, okay. So adding this 0 does not give us steady state errors as 0. Now let's say in this system, instead of 1 as the controller, sorry, let's say I used 1 by s. That is, I added one integrator to the open loop transfer function. Then what will the steady state error be? This
Infinity.
is s. Yes, correct.
Infinity.
Yes. and that is limit s goes to 0, 4 into s plus 2 by s into s plus 2 is cancelled. So this is infinity, that is ESS equal to 0. So now you see again that thing. Adding one integrator to the system helps us to achieve zero steady state error. Okay, is that clear to everyone?
Yes, sir.
Yeah.
Okay. Okay, now again to the same system, if we have a 0, if we add a 0 at s equal to 2, not minus 2, at s equal to 2 with the controller as 1, what will the stability of the closed loop system be? So first tell me, what should g of s be, the modified g of s? Original was 4 by
4 into s minus 2 by s square plus minus 2. Sir.
Correct. So okay, before doing the math, tell me, what do you think the stability of the system should be?
Unstable, sir.
Okay, why do you think that?
Because there is a 0 in the right half of the S plane.
Correct. So
सर ओपन लूप तो सिस्टम अनस्टेबल है, क्लोज लूप को सिस्टम स्टेबल भी हो सकता है, अनस्टेबल भी हो सकता है। उसके लिए मुझे बोर्ड पोर्ट या प्लग पोर्ट से देखना पड़ेगा।
yeah, correct. Let's first find out the closed loop system. So we are assuming unity feedback. So
ये अनस्टेबल ही होगा सर।
हाँ, ये वाला अनस्टेबल होगा, बट इन जनरल
सर अगर हम उस तरह से जो निकालते हैं सर,
हाँ,
एस स्क्वायर प्लस 2 है, एस स्क्वायर प्लस 6s माइनस 8 जो इसका कैरेक्टरिस्टिक इक्वेशन है सर, और एक जो रूल था सर राउथ हर्विट्ज के जस्ट पहले वाला सर, कि अगर इसमें कंसेक्यूटिव कोएफिशिएंट किसी का भी अगर जो कि निगेटिव आ जाता है सर, तो वो अनस्टेबल हो जाता है। अगला अनस्टेबल करने के लिए कंडीशन मतलब फुलफिल कर देता है सर।
करेक्ट। So okay, tell me, what should the closed loop transfer function of the system be?
सर एक और तरीके से इसको देख सकते, सबसे पहले क्लोज लूप का कैरेक्टरिस्टिक्स इक्वेशन निकालेंगे सर, फिर राउथ सर्विस क्राइटेरिया से देखेंगे फर्स्ट कॉलम में मेरा कोई सब
हाँ, वो कर सकते हैं। 1 plus gs, let's find out 1 plus gs equal to s square plus 2s plus 4s minus 8. So this is s square plus 6s minus 8. तो इसको राउथ हर्विट्ज करते हैं, s square s1 s0, so 1 6 minus 8. Now what should the value here be? minus
8.
So यहाँ हम देख रहे हैं कि 1 sign change. This implies 1 right half plane pole. So, but either way, this characteristic equation is just second order. So you can directly compute the roots as well and see that one of them is in the right half plane. Okay, another way we can think about this is, let's say the transfer function is s minus 2 by s square plus 2s, and we are just using a proportional controller, okay, that is some k. Then how do we stabilize the system? We can draw the root locus, right? Correct? So help me draw the root locus.
Yes. Add the plus 2, there will be 0 sir.
Oh, sorry. Yeah. So how should the root locus look like?
One pole goes to 0 sir, and another pole goes to infinity.
Minus.
Yeah. So this is the root locus for this given system. So here do you see that for some value of the gain we have a stable system? Is there any such case?
Yes sir, minus 1.
K, sorry?
If we put k equal to minus 1 sir.
Oh, okay. If we have a negative, then I think yeah, it will be, this part will have this, then there will be a breakaway, and I think one will go this side and the other will go to infinity or something like that will happen, I guess. But yeah, this should be the case, right?
Yes, sir.
Okay, let's find it out. Tell me the centroid. And asymptotes.
So centroid is minus 0.5, sir.
Minus 0.5, okay. And what are the asymptotes? The asymptote should be along the negative x-axis, I guess, real axis, right?
Yes, sir.
So I think we will get something like, and this one will maybe come like this, and this will be going to 0 here, something like that, maybe. No, no, no. This won't be symmetric about the real axis. No? Let us look it up. Just a minute.
So
Uh-huh.
we will use open loop transfer function for the root locus, sir. Then will -1 satisfy the case, sir, for the system stability?
Yeah, we need to check about that. Just give me a minute. Yeah, hold on. I'm sharing my screen now. Can you see my MATLAB screen?
Yes,
Yes.
Yeah.
yes.
So, if let us say, so this is our open loop transfer function, right? Now, if I plot a regular loop locus, then we have, let me dock this for now. Yeah, can you see the plot?
Yes, sir.
Yeah, so this is as we had found out, the root locus plot will be between 0 to 2 and minus 2 to minus infinity. Now we want to find out, say for, let's say at the gain value minus 1, then where are the, I'm sorry, just a minute. Okay, just a minute, my computer has gotten very slow due to sharing the MATLAB. Yeah, can you see my MATLAB screen now?
No, sir.
You can't see it now. Okay, just a minute. This is taking a toll. Stop presenting. Present again. MATLAB. Yeah, can you see it now?
Yes, sir.
Yeah, okay. So now we want to plot for some gain value, let's say 10 to 0. So if I plot that, yeah, you can see, yeah, okay. So here what is happening? We have a root locus in the real part between minus 2 and 0 as we had thought. Then they are breaking away and both are going towards the right side. Okay, yeah. So the mistake we did was we assumed the asymptotes to be along 180 degree, but that is only the case when we have a positive gain root locus. But for negative gain, it will be along the zero, like real axis, the opposite of 180 degree.
सर one second सर
Yeah.
ठीक है सर
Sorry.
अभी क्या बोले सर गेन पॉजिटिव के लिए और नेगेटिव के लिए
हाँ, गेन पॉजिटिव के लिए असिम्प्टोट का फॉर्मूला बोलो.
असिम्प्टोट या असिम्प्टोट एंगल
इधर असिम्प्टोट एंगल का
2q plus 1 into 180 degree by number of poles minus number of zeros.
बट फॉर पॉजिटिव गेन रूट लोकस वो फॉर्मूला हो जाता है बस k पाई, राइट? 2k पाई.
What?
For a root locus with gain value negative, what is the formula for angle of asymptote? सेम नहीं होता ना. एंगल ऑफ असिम्प्टोट का फॉर्मूला कैसे आता है बोलो?
प्लस माइनस 2q plus 1 into 180 degree by number of poles minus number of
नहीं, लाइक डेरिवेशन कैसे होता है?
derivation.
Like how do we find out, like वो जो asymptote का एंगल होता है basically when the gain goes to infinity, which direction should the poles be in? That is the thing, right? So for positive gain value, let me share the book. 1 minute. Yeah, hold on just a minute.
Okay.
Okay, I'll share this just now. Yeah, so look at this. This is the normal noise book. So for positive feedback systems, the change that happens is you do not equate, like for negative feedback systems, you had 1 plus kgh, correct? So for that case, the kgh open loop value was equal to -1, that is 1 at 180 degree. But here kgh has to be equal to +1, that is 1 at 360 degree, or like any multiple of 2 pi. So for that reason, the behavior at infinity changes. So if you go through that derivation, which is there in the yeah. So here you see the angle of asymptotes becomes k2 pi by number of finite poles minus number of finite zeros. Okay, is that clear? So here the asymptote will be along 0 degree. Okay. Yeah. So after that, what will happen is, so basically both the roots will go towards 0 degree, and if we plot this further, where is it? And now I plotted this only for gain value 0 to -10. If I say plot for 100, then what will happen is, yeah, you see this. Okay. Uh, do you see this, the root locus?
Yes.
Yeah. So here what you can see is this glitch is due to a slow step value. But if you take fine enough step value, what you will see is from -2 and 0, the poles, open loop poles, the root locus will come, they'll meet at the real axis, break away, then meet further in the positive real axis, break in, then meet the 0. Okay. So that one asymptote will go to plus 0 degree. Okay, is this clear?
Yes.
सर
Yeah.
इसलिए हम लोकस में k का वैल्यू 0 टू इंफिनिटी के लिए पाए थे, लेकिन नेगेटिव के लिए वो मुझे नहीं थोड़ा समझ में आ रहा था। जब गेन का वैल्यू नेगेटिव होगा तो
जब गेन का वैल्यू नेगेटिव होगा बेसिकली, तो रूट लोकस में क्या होता है? ओके, आई शेयर, ओके, आई जस्ट एक्सप्लेन दिस। सो रूट लोकस में क्या होता है कि वी हैव 1 plus kgh as the characteristic equation, right?
यस।
So for root locus, what we do is every point in the complex plane that satisfies the characteristic equation being 0, वो part होता है root locus का, correct?
Yes. Yes.
So for that we equate kgh equal to -1. That is kgh equal to 1 at 180 degree. Let me share this. Yeah, you can see my writing pad, right?
Yes.
So for normal root locus we have this. This implies kgh equal to -1, that is 1 at 180 degree. So from there we find out rules where on real axis it should be, where on like what the asymptote angle should be and all that. Like if this were a positive gain root locus, the root locus should be on this branch of the real line, not on this branch. Correct. But for a
Yes.
negative gain, it will shift. You can check up the rules in that normalized page that I showed. From there, you'll get the entire list of things. If I go explain that now, it will take quite a lot of time. If you go through that, if you have any doubt in it, then we can discuss it later. Okay?
Okay.
Yeah. So what was this question originally? Yeah. Is the closed loop system stable? So here we see that it is not stable as there is one sign change in the route array, and so that implies there is one right half plane pole. Now moving on to the next question. Consider the feedback system shown in the figure. The process transfer function, this one, which corresponds to some actual system plant, is marginally stable. Okay. And we are using a PD controller to try to control the system as per our requirements. So first find the characteristic equation of the closed loop system. So the open loop thing becomes so tell me the characteristic equation for this GFS.
Yes, sir. A square plus 10 plus 10 SKD plus 10K.
Correct. So S square plus 10 KDS plus 10 KP plus 1. Correct? This is the characteristic equation.
Yes.
Now we move on to the next question. Take tau as, it is being continued, okay. Take tau as Kp by Kd and let the characteristic equation be expressed in this given form. So we had this as the characteristic equation. Yeah. So express it in this form. 1 plus some constant into n of s by d of s. So since tau is equal to Kp by Kd, we have that Kp is equal to tau Kd. Okay. Now using this, tell me what this should be in that form.
A square plus 10 KDS plus 10 tau KD plus.
Now that is true, but represent it in this form, like we did for root locus.
सर इसके लिए सबसे पहले तो 1 प्लस KD को कांस्टेंट लेंगे और
So first KD को कांस्टेंट लेंगे और
सबसे पहले KD को कांस्टेंट लेंगे सर, जो भी टर्म है मतलब A स्क्वायर प्लस 10 प्लस KD इंटू समथिंग। यस सर। उसके बाद इसको डिवाइड कर देंगे सर 10 KD इंटू एस प्लस टाउ बाई पूरे टर्म को डिवाइड कर देंगे एस स्क्वायर प्लस।
So this is how we get the characteristic equation into this desired form. Correct. So अभी क्या होता है कि now we can use root locus technique.
डिनोमिनेटर में h स्क्वायर प्लस 10 होगा ना सर, only.
Yes.
Sorry,
Yes.
sorry. Yeah. Denominator by s plus 10. Yeah. So now what we can do is we can use root locus techniques and results on this given characteristic equation with kd as the variable gain. Right. So from that we'll see how we can use it in the next question. So we are given that tau varies from 0 to root 10. Which of the following statements are correct? So from amongst these statements you can see a few things, like what we are being asked is, as tau goes to 0 or as tau goes to root 10, what is the value of the pole, the dominant pole, as the gain value goes to infinity? So this is a very clear question, like we have something of this form, right? So this is 1 plus some gain into some open loop transfer function, let's say h of s. So as the gain goes to infinity, we know that one of the poles, open loop poles, will go to the open loop 0. Correct. So now n of s is s plus tau into 10. D of s is s square plus 10s. So here again you see there are
S
two poles.
square plus 10 only.
S square plus 10 only.
Sorry, I'm making the same mistake. So here you can see that s square plus 10 is a two pole system, like there are two poles in the system and there is one 0. So one pole will go asymptotically to infinity and the other pole will go to the 0. Okay, and since one pole has gone to the infinity, clearly the dominant pole will be the one that goes to the 0. Right. So as kd goes to infinity, the dominant pole approaches the 0, that is s is equal to minus tau, and as tau goes to 0, that will be s is equal to 0, and as tau goes to root 10, that will be s is equal to minus root 10. So as tau goes to 0, this is one option, and as tau goes to 0, this is the other option. Is this clear to everyone? Yeah? We are clear on how we got this?
Yes.
Okay. Yeah, is anyone saying something?
Sir, is there any formula for dominant poles if we have multiple poles?
There is no formula for dominant poles. We just take kind of a thumb rule that if the pole is near to, like, say one pole or a pair of poles are at least 5 times nearer from all other poles. Let's say we have something like this and one pole here. If this distance is 5 times this distance, then we will say that these poles are dominant, these two poles. But say if you have some doubt in this question, let's say, like where do we have? We have poles on plus minus j root 10 and 1 0 at some tau minus tau. Right. So again here how many asymptotes will have? We'll have how will we have this system? Tell me. How will we have the root locus for this system?
One ends at the zeros and another goes to the infinities.
Yeah, that is correct.
रूट लोकस का पार्ट है सर ये जीरो के लेफ्ट साइड में से, और एक जो पोल है वो जीरो के पास आएगा सर, और एक दूसरा जो होगा वो इंफिनिटी के पास, मतलब वो आएगा सेमी, मतलब यस सर, जस्ट लाइक
something like this. Yeah, this should be the root locus, right? So here you can see as gain goes to infinity, मतलब पूरा एंड पॉइंट के अराउंड, ऐसे के जीरो से बढ़ के ऐसे पूरा जा रहा है, के जीरो से आके ऐसे आ रहा है, तो as k goes to infinity, clearly ये जो पोल है जो दूर गया, that would be very far away, and the pole that came to the zero, that is only at minus tau. So clearly this pole, the pole here, that is a dominant pole. We can assume that, right? Because the other one would be much farther away. Yes? So in this question we don't need anything to decide the dominant pole, because that is evident from the root locus plot. Is it clear?
Yes.
Okay. So next we move on to the next question. Now for that same set of this process like plant and a PD controller, I want to find out a PD controller that meets the following specifications. That is, percentage overshoot is less than 5% and the settling time is less than 1 second. So now we are given 4 controller values, 4 feasible controller values, and we want to find out the one that satisfies these two. Okay, so for this we'll again use MATLAB. So I'll share my screen.
विदाउट मैथ्स सॉल्व कर सकते हैं?
हाँ, without MATLAB भी solve कर सकते हैं, बस the calculations will become very tedious and time consuming. You can try it out, you can verify it out for yourself, but like ऐसा MATLAB जरूरी नहीं है, but it is.
We have to find.
I'm sorry,
we have to find for all these 4 values.
Yeah. उसी लिए I'll
We have
use
to
MATLAB.
find for all these 4 values of KP and KD.
Yeah, we have to find out whether each KPKD satisfies this or not.
It will take more sense.
Yeah, that is only I'll be using MATLAB to show how we can do that. Okay, so in exam you won't be getting questions like this, you'll get things that you can solve. So this is just to explore how to do things and all. Okay, are you guys familiar?
Examinations, sir, MATLAB is a lot.
No, in examination you don't need to use MATLAB. Like questions will be such that you can solve with pen and paper. You don't need to worry about things like that. This is just to learn more about the subject. Now, how many of you are familiar with MATLAB?
Are you familiar with this one?
Okay, I'll walk you guys through this. So, look at this part from PD controller design. So this function TF, what it does is, it gives us a transfer function with numerator given by the polynomial. Okay, I'll just do it this way. Can you see, look at my command window, okay? You have a. So what this does is, it initializes S as our transfer function value S, okay? Then I'll define G as, what is the plant we have, 10 by S square plus 10. So G is equal to 10 by S square plus 10. Correct? So this is our transfer function we get, 10 by S square plus 10. Now to that transfer function, we want to use a PD controller. So any PD controller, let's take the first one. The first one, KP and KD values were 3 by 5, that is 0.6, and 1 by 10, that is 0.1. Okay. So it is KP 0.6 plus.
तो कमांड है नो नहीं दिख रहा, स्क्रीन विजुअल है सर, बट वो जो आप कमांड लिख रहे हैं वो नहीं शो कर रहा।
अच्छा, जस्ट अ मिनट, हाँ अभी कमांड दिख रहा है?
Command window is visible, sir. But
Now,
what are you writing is not visible.
now can you see I increased the font size? Is it visible now or should I increase it more?
So we are only seeing that S equal to TF into S bracket S.
हाँ उसके नीचे का कुछ नहीं दिख रहा है क्या?
No,
No,
sir.
Okay.
Maybe your screen may be paused.
Yeah, wait, I'll just reshare this. Yeah, is it visible now?
Yes, sir. Now visible.
Yeah, okay. So we initialize G as the plant transfer function 10 by S square plus 10, okay? Then I'm using some GC1, my first controller, that has the given KP and KD values. Okay, 0.1 S plus 0.6. KD is 0.1, KP is 0.6. Now what I do is, we can find the information about the step response just a minute. The information about the step response from this. So see, this feedback function, what it does is, we have G into GC1 as the open loop transfer function, and this 1 gives us the feedback gain. So that is unity feedback in this system. So this feedback, let's first do that. Yeah. So this gives us the closed loop transfer function, right? So now with this, what I'll do is step info. So this will give me the details about everything. This is the rise time, this is the settling time, this is the percentage overshoot, and this is the peak, and this is the peak time. So now we can also wait. So this is our closed loop transfer function, right? Now what I can do is I can see what will be the step response. Yeah, I'll share this one minute. Yeah, can you see this now? The step response?
Yes, sir.
Yeah, so here you can see that the percentage overshoot is almost 82%. And what was the other requirement that we had? The other requirement that we had was that settling time should be less than 1 second. So here settling time is 7.8 seconds. So this satisfies neither of the requirements. So next controller that we had, it was for GC2 is equal to 1, that is S plus 6. Okay, this is the next controller. So TC2 will be feedback G into GC2 1. This is the new closed loop transfer function. So here again we'll do step info TC2, that will give me this. So here again you can see settling time is less than 1 second, that's good, but overshoot is 31%, which is, we want that to be less than 5%. So here if I plot the step response, so you see this, even though it, oh sorry, yeah, so here you can see, even though this is much better than the last one, it settles faster, it also has lower overshoot, but it still does not meet our requirements. Is that clear? Okay, we'll just do the other ones quickly. GC3 is given as 6 into this plus 36. So TC3 as this. PC4 is 1378 and TC4 is yeah. So now we have to compare the last two. Let's see the plots first. TC3. So this plot, when you see, you can see that this also settles clearly within 1 second, at least some 0.3 seconds around. But this has some overshoot. We'll have to check how much exactly. And we can see step of TC4. So that is now, this is even better. It settles faster and also has very little overshoot. So now we can see the information about it. Step info TC3 and step info TC4. So for TC3 you can see that settling time is 0.32 and which is well within our requirements, and but the overshoot is 9%. So we still want better. Now for TC4 you can see settling time is just under 0.2 seconds and the overshoot is 4.7 seconds, which is less than 5 seconds. So with this, the final I'll share this screen again. Yeah. So with this controller, that is with KP13, KP78 and KD30, we get our desired.
MATLAB file with us.
Yeah, I'll attach it with the slides. Okay, so is it clear? You guys can go through the MATLAB code and play around with it, because MATLAB is a very convenient tool for actual purposes. Because when you have to design a real system, you won't be doing everything by hand, you know. And but doing everything by hand has its own merits. It gives us a very good understanding of the actual working of the techniques that we use. So once we are clear with that, we can switch on to MATLAB or some other programming software and can visualize things much more easily than doing it with hand. So with that we end today's questions. So does anyone have any doubts? No doubts? It is
Yes.
okay. So what do you mean, Yashwant, by accessing MATLAB? Like, do you want me to give you a rundown on how to use MATLAB for control systems, or how is it? Okay, maybe after we are done with the regular assignments, in 1 or 2 classes after that, we can see how to explore MATLAB and stuff. Yes, because now you guys need to submit assignments every week, I suppose. So yeah, we'll do it after that.
और बेसिक बता देते सही कैसे मैटलैब को यूज किया जाता है.
MATLAB को कैसे यूज किया जाता है, as in, okay, I'll share this. So see, are you guys familiar with any type of programming language?
Yes, FPS price on this circuit solving.
PSpice is not a programming language, it is just a simulation.
No, sir, programming. Yes, simulation.
Yeah. दूसरा वाला क्या बोला?
मैंने PS टाइप बोला था एक ही.
Okay. So, okay, then there are many tutorials, proper tutorials, but if you just want to explore MATLAB, say you download MATLAB, okay, and then here you can see a very MATLAB. One very good thing about MATLAB is you can search up anything, and they have very nice documentation. So let's say control system, or let's say transfer function. So which screen is visible to you guys? Oh. Okay, I'll share this other screen. 1 minute. Yeah, can you see the screen?
Yes.
Yeah, so if you go to the transfer function model, yeah. So here you can see the entire thing, like it has a very nice description for what the transfer function does. Then you can see how to use it, like this is equal to t as something. So then you'll see you have to give a numerator and denominator polynomial. Then there are examples as well how to do that. Where is that? Examples. Mm, okay, this, yeah. Yes, sorry, this is getting very laggy. Okay, here you can see, like, to define a transfer function, what possible methods you have, how you can define it by either a numerator denominator polynomial or by initiating an s variable like I did in the examples. So you can explore around with the documentation of MATLAB and see how you can go. Then, okay, let's search for how to plot the root locus. Okay, there is this root locus. So then it says, suppose you give a transfer function and type R locus, like you define this transfer function by this command, then say type R locus of that system. That will give you a nice root locus. Then further commands are there, how to plot multiple system models and how to look only for a certain gain range of things and so on. So you can similarly, okay, let's take this Nyquist. So again, this you see, you have a given a transfer function, you can plot a Nyquist diagram. Then you can also get other values from the Nyquist diagram and stuff like that. So you can explore around with the documentation and play around with MATLAB. Then when we get around to a session where we discuss MATLAB, we can go in more details. Okay?
Yes.
Okay. So with that, we'll end today's live session. So solve as many questions and then we'll meet next week, Tuesday, same time. Thank you.
Thank you.